All right, thanks for letting me come. This is really exciting. Full house. So my name is Bill Pierce. I came down from San Francisco, and it's cloudy and cold there. I got off the plane, went out to get my rental car, and gosh, it was so nice. I took off my jacket. I said, man, this is beautiful. And the woman giving me the car said, what are you talking about? This is really sucky weather. It's so, so cold. So you obviously take it for granted. But it's fun to be here. Just a little background. The reason I'm here is a friend and I were doing a hackathon project that was sponsored by Intel. And I'll tell you about the details of the project, but Intel liked it enough, they asked us to go to some various meetups. They said, we'll fly you, we'll put you up in a hotel, and you can give your little talk. And as long as the word Intel Edison comes up from here, from time to time, you're good to go. So I'm not really going to emphasize the Edison too much, but it is behind what we did, and it's a cool product. We do have a Raffle, the second Raffle. This is a Basis watch. It's a company that Intel purchased. And this is the older version, but it's free. So one lucky winner.
Okay, real quick, our Twitter handle is JS.LA, but if we're just going off of the Intel maker.
I can fix this so fast.
Sweet. All right. We have the technology. Yeah. Do it live.
Is that accurate?
Yeah.
Sweet. Okay, so if you don't mind, if you are inspired, then sometime during the talk, just tweet something about the talk, something funny, clever, constructive, critical. Just remember, I'm the one judging. This is the agenda. I'm going to come back to this from time to time so that you know if we're making progress. To start out, I want to give a little overview about intelligent devices and start with a couple hype slides. Here's a hype slide from Hans Moravec. He's a roboticist at CMU, projecting, I think this is around 2011, where things are headed just with processing power. And it looks like here in 2015, we're, somewhere around a mouse or monkey. So mice are pretty smart, but it's getting better. Here's another hype chart. This is from Gartner, the hype cycle for 2014. Look what's at the very top. This is the peak of hype before you enter the trough of disillusionment and hopefully recover to the slope of enlightenment and plateau of productivity. We'll see how it goes, but it's at the top right now. Well, hype aside, this is actually a pretty fun time to be working with devices, with intelligence. These little computers, they're so cheap. Anywhere between $35, $75 will get you a nice Linux single board computer. I've heard talk about a $9 Kickstarter project for a Linux computer around the corner. And not only that, but the tools to build intelligent systems are really good too. I'll talk later about some of the tool stack that supports machine learning. This is the same tool stack that academics use, and it's all free, open source, and there's plenty of information on how to use these tools. And of course, you all know about Node.js. Pretty much all of these cute little devices run Node.js, usually out of the box. So it's a fun way. If you haven't played with embedded systems before, you can start with what you're familiar with. Here are a few examples. There are more out there. The BeagleBoard, the Raspberry Pi. The Arduino doesn't currently run Linux, though there's a future version that will. And then some of you may have heard of Tessel. This one really does focus on Node.js in particular, though the others support it. And then the Intel Edison gets its own slide. This is the one that I've been looking at. The difference, here's some breakout boards that come with it. The main thing that makes this Edison stand out for some applications is just that it's really small. You can kind of see by comparison. But it really depends on your application, what you're going to want to work with. Raspberry Pi, Bigger boards, Tesla, Edison, they all support Linux. The Edison is smaller. It has Bluetooth and Wi-Fi without adding shields or capes. The Raspberry Pi is probably better if you want to do audiovisual applications and just keep your eyes on the horizon, and new devices are coming around all the time. Okay, this is a summary chart we can come back to if people have specific questions about some of these parts. But the bottom line is it's a 500 megahertz processor, a gig of RAM, 4 gig of flash, and it runs a version of Linux, the Yocto Linux. Okay, and I'm actually not going to get into Node.js, but this is just sort of an example of what you might do with one of these devices. Kind of the hello world of embedded devices is blinking a light. And this code will do that. In the case of the Edison, they provide bindings for C++, for JavaScript, for other languages. So in this case, we require MRAA. It's their library. And then using that, you can define an object for a general purpose I/O, number 13. And then turn it on and off once per second. There you go. It's a hello world. Now, I don't know if some of you have heard of Cylon.js, but this is a company that's really getting into JS for embedded applications. And they allow you to abstract the particular device for projects that you might be working on. So for example, there's nothing here about MRAA, although this could work with the Edison, because they've provided the lower level wrappers. And you can do something that looks pretty much the same for a lot of different devices. Here you're providing a JSON structure to characterize what you have. This is the Edison version. There are many others. And again, every second we're toggling a little light. That's just a high-level flavor. And the sort of things that you can do with this, there's just a ton out there. Here's a few examples from the Cylon.js page. Cameras, rangefinders, servos, LEDs, of course, compasses. And I don't know what all those things are on the right, but if you need them, they're there. Okay, so that's the introduction. I want to talk about this particular project. So my buddy Clarence and I, and actually another friend, Cesar, did this hackathon in Mountain View last September. And the idea was to use the Intel Edison. And the concept that we came up with was, let's see if we can collect audio data from a bicycle. Listen to the cassette, the derailleur, the chain, and see if using that information we can predict when it's time to tune up your bike. That's the concept. This is a weekend hackathon, by the way. So for the, I'll get into what we did actually at the hackathon, but this is just a summary that we can come back to, the concept. And what I'm going to talk about tonight for the main part of the talk is this approach that we ended up taking. What we did for the hackathon was really just a prototype. And Node.js was actually very useful for that. What we realized, though, is that to do something truly useful, or at least with more promise, you need to step back after you do the prototype and see, well, what really makes sense for an architecture. And then once you've got that in mind, then you can actually move forward and do some development. So I'm going to talk about these three aspects. First of all, the prototype. The idea was to start with what's familiar, with what you have at hand. I hope this isn't too small to read. But what we put together in that weekend was really the infrastructure, no intelligence, nothing to do with machine learning. But the infrastructure to demonstrate what that would look like. So we had, on the audio data collection, a sample audio function, some JavaScript to look for changes in the file, publish those to a client, to a server, and then on the server, we would have the human in place of the machine learning algorithms look at this data and say, yeah, it looks like it's time for a new chain, and hit the button. That would go back to the device, and the light would blink. We know how to do that. So here's some of the technologies we use. We had MongoDB on the server, Angular, jQuery, Lodash, Bootstrap, WaveSurfer.js. Cesar was a client guy, and he was very good at, well, he's very good with Node.js as well. So throwing everything from NPM that he could think would possibly be useful. And we had a pretty impressive little demonstration. But all just because of the power of Node and the ability to prototype quickly. So here are a few pictures of the project. The Intel is this little board here. The breakout ends up looking kind of like an Arduino. It actually has Arduino connectivity, so you can put this shield on top and easily wire up various sensors. Here's our check engine light, and here's a little microphone. That's the installation using a bento box and wire wrapped around the frame. Here's the audio. I'm putting it in quotation marks because it turns out that as it stands, the Intel isn't so good at pulling in real audio. The SPI that controls the ADC is just too slow. So we ended up with something that looked like this, and it's really a mystery what that would mean. But you could scratch your head, look at it, and say, yeah, it looks like it's time for a new chain. And here's the paparazzi filming the event at the end. OK, so that's a prototype. Now, when Intel asked us if we'd be willing to continue to talk about this project, that was motivation to keep working on the project. And that's where the architecture comes in. Stepping back and thinking about, well, if we're really going to try to experiment with machine learning, what would that look like? Here's the original concept. You pull in the data, some machine learning AI miracle happens, and out comes the result. What does machine learning really look like? Well, here's one thing it kind of looks like. You got some work to do. Here's the bicycle upside down in the apartment, and you're collecting a lot of data. I actually did a fair amount of this, running the chain by hand, pedaling by hand at very specific speeds using a little metronome on my iPhone. And I did one experiment with 8 different gears and 2 different speeds to collect a lot of this just raw data. And it's labeled data because I have all the data I've collected, and each time I collect it, I say, OK, here's this particular gear at this particular speed, and you can trust me, that's really what it is. The next step is to come up with feature extraction, something that a machine learning algorithm can work on. So what machine learning is, if some of you aren't familiar, it's kind of like statistics. It's kind of like a black box of magic, if that's how you'd care to approach it, because in some cases, these tools allow you to actually approach it that way. But what you need for the black box, or for the thing you actually do understand, you need features to give the system. And for supervised learning, you need features together with labels. So the idea here is, here's some features that capture this particular 10-second audio sample. And here's the label that says it's my highest gear at 60 strokes per minute. Now, if you've got a clean data set, then there's some work involved in experimenting, coming up with a model that captures that relationship between the features and the data so that you can actually build a classifier. If you have a classifier, then with new data, you can extract the features in the same way and apply it to the model and come up with a result. That's the idea of machine learning, in our case, at least. All right. So if we're talking about an architecture, the question becomes, well, how do you map this onto your system? Our our concept for the prototype was, oh, by the way, just to finish the goal here, our vision was your classifier could tell you, okay, this looks anomalous, you better check the engine. But as far as how to implement it, the original concept was, we'll pretty much do everything on the cloud. And there's some advantages to that. But that's what this would look like. The data would come from the bike. It would just be pushed to the cloud. The cloud would take the audio, extract the features according to the best approach to do it that day, and run the classifier. The thing is that these little processors are pretty powerful, and you've got other choices. So for example, you could actually put all of this on the device. Certainly the Intel Edison and some of these other devices are powerful enough that they can do the feature extraction. If any of you are familiar with Fourier transforms, that's what we're doing here, is taking fast Fourier transforms of this audio data to, it's kind of like breaking it down into the frequencies, sort of like a graphic equalizer. Here's the feature sets that we're actually using for this experiment is, imagine a graphic equalizer with 10 different channels, and you see the intensity with each of those frequency sets. That's the sort of feature sets that we're dealing with. So you could put all of that onto the device. And there's even more that you could do. So with the previous approach, you're coming up with this particular model. Think of it as this machine learning black box that takes features in and gives you a classification out. But you could even consider putting some of that onto the device itself. And this is a longer term goal, is anomaly detection, where you have the device maybe not be so smart to start out with, but just continually monitor what it hears from the bicycle, build a statistical model, and then when it has enough information that it can reliably say, okay, this looks like an outlier, now that's the reason to turn on the check engine light. So that's kind of more of to me, that's a more cool idea because it's putting more of the challenge into the device. Okay, so that's the architecture. I guess the point is there's really trade-offs to make. And moving forward to development, the idea here is, well, let's go with that sort of middle ground where we collect enough data to make a classification and then run that on the device. So I want to talk about what development can look like. And my target here is some of you kind of get excited about using some of these embedded devices with Node, and then you want to consider pulling in machine learning. Here's some things that are lessons learned that might be of use. Well, one lesson learned, although it's pretty obvious, is that what you deal with one of these little devices, the concerns there are different than the concerns associated with this machine learning task. So if you can separate those, you'll be better off. So for example, with machine learning, you're trying to figure out the architecture, coming up with these features that can be a challenge, deciding what algorithms to use. You don't want to be tripping over all those hardware issues like battery life, or is the hardware even stable yet because maybe the hardware team is just on version 1 right now. And you don't want to have everything run slowly because of limited power, limited CPU. But to do that, you need to justify it. If you're going to come up with a solution by working on a comfortable host, like a MacBook Pro, say, but you want to know that it's going to work on your actual device, you need to characterize how those compare. And so here's an example of some comparisons. You can see the Edison's a lot slower than a MacBook, but it's not too slow. Here's an example where we've got 10 seconds of data. It's taking over a second to do this fast Fourier transform and come up with these features, but it's got 10 seconds, so it's enough. Here's 1,600 seconds of data, and it's taking 110 seconds to do some feature extraction. Doing the training and the classification is actually quite efficient. So the bottom line from that slide is, yeah, it looks like we could go ahead, develop on our host, and be confident that we'll be able to run it on this little part and have it behave well. So maybe I won't get into these details too much, but Another part of that task, if you want to develop where it's comfortable and know that it's going to work well on your device, you need to come up with similar environments. So for example, the Mac is good because it's Unix, and the device runs Linux. One challenge that we had is, like I said, the Edison isn't so good for audio, but that was easily solved using one of these tiny USB sound cards. I mean, the whole thing is about this big, and I could use it both on the Mac and on the device, and it worked fine for pulling down real audio files. It actually involved rebuilding the kernel to make that work, but once you get past that, it's cool. And then, of course, you want a common tool stack, and if possible, setting up Git so that it can maintain all your software and do that on the device. There are some tricks that make that easy without actually having to run Git on the device. So those are details. All right, the next lesson is, again, we're on this, remember we did the prototype, we came up with an architecture, and then we're going to develop. So the next idea here is figure out the right tool stack to use. And I know this is a JavaScript crowd. So how many people are familiar with Atwood's law? A few of you? Any application that can be written in JavaScript will eventually be written in JavaScript. Attributed to Jeff Atwood from the Coding Horror blog. Well, in fact, let's just do a search for machine learning at NPM. 2,940 results. Machine learning, ML, machine learning lib, Node, ML. Oh, machine learning. This is just the first page. Well, so the good news is if you want to just get in and play around, you can do some research, figure out which of these are mature, and play with them. Why not? But I would say if you're serious today about moving forward quickly with machine learning, this might be one place where you want to use what the cool kids are using. And this is Python. Can I say that word here?
Yeah.
OK, great. This is a Python-based stack that academics use for machine learning. My wife is actually a machine learning academic of sorts, and I took it from her. But you can see there's a lot of literature out there. And in our case, here's a particular stack that's very easy to use because the Continuum.io supports this Anaconda, and they maintain repositories, so it's easy to pull down what you need. I've highlighted in green the things that we found useful for our project: NumPy, SciPy, Matplotlib, IPython, and scikit-learn. And this, I won't bore you with the details, but one nice thing about Anaconda is that there's a Miniconda version, and that allows you to target embedded systems with a little bit more control about what it pulls in. So you can come up with much smaller footprints. And that's what we were able to do on the Edison. I'm running the same stack as far as what I need right on the Edison. So it's got Python, NumPy, SciPy, scikit-learn. These are for math, statistics. Scikit-learn is just a lot of good tools related to machine learning. OK, so to finish the development part, I've got a couple sets of examples to give you a feel for what that looks like if you guys decide to jump in and start working with machine learning. Data analysis. Here's some specific examples. You remember those audio files in quotes that I put up earlier? Okay, so this is real audio. And here's 10 seconds of audio from my bicycle. Here's zooming it in. So this is 0.2 seconds. You can see it actually, you can imagine that corresponds to a bike cassette that's turning at a certain speed. the nice thing about these tools is it's very convenient for examining. If you want to, I've mentioned that machine learning can be treated like a black box, but really you're always best off if you understand as much as possible, because these algorithms can be good at figuring things out, but it's best if you kind of have a good intuition in advance that a human could also figure it out. So using these tools, you can look at some things and see, okay, here's, for example, 60 revolutions per minute. Here's 75 revolutions per minute. Everything else is the same. Could I expect my machine learning algorithm to figure out the difference? Well, here you can look at it and say, well, yeah, the signature actually looks kind of different. And this is a Fourier transform, so we're looking at frequencies here. And you can see, yeah, here's some fairly low frequencies that are actually shifting as you go faster. So it looks like you have some data here that could be useful. And again, this tool stack is very useful for making that case. And it can also help you visualize problems that you might trip over. Remember I said that the host needs to be pretty similar to the target. Here's something that I saw on my host platform. This is at 60, this is 120, this is 180, this is 240. Can anyone tell me what that probably corresponds to? Yeah, it's just harmonics and the fundamental of these lights, or whatever. It's the 60 cycle power. So something to watch out for. Obviously, that has nothing to do with riding a bike. But with this view, it's very obvious what you're dealing with. Final section here on developing. So we looked at the data, and we kind of saw that as humans, we can look at this and see some features that might be useful. Can we actually run a machine learning algorithm that does something useful? So here's just a few slides on using the scikit-learn package. And I won't talk about these details, but what we have here, because this stack is written in Python, it's easy to write scripts, to automate things, to try experiments. So here's an experiment where we come up with, taking the audio data, think of the graphic equalizer, let's just break it into 4 bins and see if you can do something useful with that. And for this test that this represents, I've collected some data where I've got 8 different gears, so 8 different speeds on the bike, and then 2 different cadences. So I've got 16 different classes, and I'm trying to see if I can train something to listen to new data, from data that I've set aside, and predict which gear and which speed. So let's try it with just 4 of those frequency bins. And you can see it actually does pretty well, 84%, just based on that. If I go up to a finer resolution, 10 different features rather than 4, I can get over almost 97% accuracy with this particular machine learning algorithm. So you give it a black box for now, but it's a support vector machine if any of you are into that sort of thing. And then here's tweaking the parameters, so you can see that our accuracy goes down to 81%. But it's really easy to do these experiments once you've got the data set up and once you've got the stack in place. Okay, that covers this approach I was talking about: prototype, architect, develop. And as far as where we're at on the project right now, these simple classification tasks look pretty promising. I talked about the idea of trying to make this thing autonomous, where it could do anomaly detection on its own, and that's still future work, looking into that. So to wrap it up, this really is a fun time to be playing with things like this. It's the tools that I was talking about. I presented a lot of stuff, but there's a lot of good information about those, and the devices are cheap. And again, this is a particular approach that we found useful. Use Node.js, whatever you've got in your arsenal to prototype something quickly, kind of build your motivation, build the vision, and then stop and really think about it before doing development. And especially at the prototype stage, Node.js was very useful. But for the For the development where we're doing the experiments, I kind of focus on Python. But for putting the system back together, again, Node.js would certainly be the bottom layer for the connectivity. I've got a few resources here. This will at least make it into the video. I know the font size is small. OK, let me just leave that one up there, if I can. Any questions? Oh, don't forget Intel Maker at the bottom. I didn't copy the JS.LA, but.
Yeah, we got a question, I think. Did you initially started off, I think, saying something about detecting broken chains? So did you have a data set with some chains broken?
Haven't gotten to that, and it kind of touches on this idea of whether to go for that anomaly detection or not, because when you're talking about detecting that it needs a tune-up or a stretch chain or a stretch chain that needs to be replaced, something like that. If you can get data on all of those failure modes, then it's actually an easier task. Because as you saw, it's not that hard to train it to recognize things that you can give it data for. The problem is bikes can fail in a lot of different ways, and you might not have data for all of that. And so, no, we didn't have data for that. The hope would be to get to something more like anomaly detection, where anytime it's doing something a little unusual, it could predict that. And the rider of the bike would have to be smart. Maybe it's the first time they went riding on a cobblestone pavement, and now the check engine light is coming on. But hopefully, if you start riding there enough times, it would have a chance to figure that that's normal. Sam.
Yes. You mentioned that one of the disadvantages of not having it on the cloud is that you can't really update the algorithms or anything like that. Are there any ways for like the Edison or anything like that to have some sort of, you plug it in and get a software update, or is that sort of things that they aren't as concerned with these sort of small portable things?
Yeah, you would want to be able to do that. And yeah, like you said, if you do go with that architectural choice where everything's done in the cloud, that's a real advantage, of course. But these devices, the Intel Edison and the others as well, you can certainly have Wi-Fi or Bluetooth. You want to be connected to the cloud somehow. How else will we serve advertising?
But you can over the air update your software, right? Should be able to.
Well, yeah, in theory, certainly. I don't know if Intel has something in place that makes that easy already, but the kind of software that we're running, we're not planning to. We wouldn't plan to update the kernel over the air. It would be the algorithms that are probably written in Python and Node that we would update. And so, yeah, you can imagine how you could do that yourself. Good questions.
One more.
Just basic questions, really. How do you? I'm just asking, how does Edison talk to the cloud? How does it connect?
It's up to you, really. Like for our for the hackathon, we were running Node.js, and it was using, I think it was Super Agent, just a Node module. Yeah. Okay, maybe that's your question. Yeah, it has Wi-Fi. So the idea is that when you set it up, for example, with a bicycle, the concept would be that you set it up for your home Wi-Fi. So when you're out on your bike ride, it's just saving data to its flash, and it has plenty of flash. Then when it comes back to the garage, if you guys have garages in Los Angeles, I don't, then it would sync up and push to the cloud at that point.
All right, any more?
Okay, good. Bill.
We,